Alright, so in this video I'm gonna be explaining another important article with the title Fast and Effective Graph Neural Network Training with Linearized Random Spanning Trees. I have talked about random spanning trees in my playlist for spectral graph theory, also in my playlist for approximation algorithms, and different playlists. But this paper in 2024 by Bonchi is very important. Very important. So we present a new effective and scalable framework for training graph neural networks in node classification tasks based on the effective resistance, a powerful tool solidly rooted in graph theory. Our approach progressively refines the graph neural network weights on an extensive sequence of random spanning trees, suitably transformed into path graphs that retain essential topological and node information of the original graph. The sparse nature of these path graphs substantially lightens the computational burden of graph neural network training. This not only enhances scalability, but also effectively addresses common issues like over-squashing, over-smoothing, over-correlation, you name it. So we carry out extensive experiments, and so let's jump into the idea. They propose I've talked about effective resistance in spectral graph theory playlist. This is very important to understand the global topology of a graph. And of course it has some computational complexity because you need to solve a system of linear equations. Of course there are some improvements to that computational complexity, but still it's a big burden, big obstacle to really make it more practical. That's why people shifted to easier approaches like kernel diffusion and many other things. So the key idea is weighted feature aggregation, where the weights are provided by the effective resistance of the edges incident to the node being classified. So the task of node classification is very obvious. And so some nodes are for training, some nodes for testing. You get the aggregation. Using this aggregation and update, you get the message passing like this. And then graph linearization. This is important. We introduce our graph linearization procedure, whose goal is to approximately preserve the information contained in labels of G in the form of its labeling cut size. That is, the number of edges that their labels are different. So this is a metric that captures the label complexity of the node classification problem. A standard inductive bias in graph learning is the homophily, that essentially posits that strongly connected nodes tend to share the same labels. But of course, this homogeneous assumption is not good. So when we have some heterogeneous graph like this one that suddenly have different labels, then that doesn't work. Then even graph convolution network doesn't work. We need to invent new kind of graph neural networks that can come up with these problems. So let's carry on. A standard inductive bias it is homophily, and I said that phi tends to be small on typical graphs, and a more refined notion of cut size for node classification that exhibits very appealing properties is the effective resistance weighted cut size, where each edges with mismatching labels is weighted according to its, this is the resistance, effective resistance between two nodes I and J. So in the interpretation of the graph as an electrical network where edges, weights, or edge conductances, the effective resistance between two nodes is just the voltage between I and J when a unit current flows. This is definition of effective resistance. So we expect that R sub ij will be small whenever there are many edge disjoint and short paths between I and J and large otherwise. For instance, if G is a social network, this effective resistance between node I and J is roughly inversely proportional to the number of common friends or connections between users. So, the largest possible value of effective resistance is 1, which corresponds to the case where I and J are adjacent nodes. And I and J is a bridge in G, that is an edge whose removal disconnects G. So R sub ij is locally density dependent in that the contribution of the edge to phi is small if I and J is located in locally dense areas and is large if it is located in sparsely connected areas of graph. The effective resistance between two adjacent nodes is also equal to the probability that belongs to a uniformly generated random spanning trees. So now phi, this effective resistance weighted cut size, this one, is now the expectation of phi. So the expected size of this expectation is of P is at most 2 times phi. This is because for labeling Y and all spanning trees, if P a path graph obtained from T via a depth first visit, then it is proven by Bianchi that this holds. So the compression is very fast to compute. Then they introduced GNN, which is graph effective resistance network. So we know the classical GCN here. D sub I, these are degree of node I. There are and W are learnable weights. This little gamma here is a vector nonlinearity, for example, ReLU. The message passing update is executed for K steps, where K is a small constant. And GNN is summarized in algorithm 1 here, that but first we have the graph, it is given, then the training parameters, maximal number of epochs, also number of hops K. Then we initialize the model with random weights. Then we generate ARST and corresponding P sub E. Then we perform a forward step to calculate the log probabilities of labeling classes for each node in the K-hop neighborhood of each node. Then cross entropy, backpropagation, log probability, cross. The rest is standard. So these are important steps that we need to focus. So the algorithm has an extra ingredient, which is the generation of RPGs via approximate random spanning trees. An approximate random spanning tree is generated through a fast hybrid method for RST. I like this paper very much because they noticed that if we get the random spanning tree, that's a very good summarization of the graph. At least you know where to go, where is your global position. You get everything. But still, you don't have information of local structural things and many other important local features. So you have a graph, then you have depth first visit of random spanning tree, then you have random path graph. So this RPG is a random path graphs that is obtained using approximate random spanning trees. And of course, it has good properties. It can handle over squashing, over smoothing very nicely. So this is the average accuracy and standard error for different methods applied to the Cora PubMed. So they use Cora PubMed dataset. There are also, for example, Colab, PubMed, Sightseer. These are important for node classification. These are benchmarks. You see in 90% of ICML papers, they compare these things. Still, we have less than 95% accuracy. Less than 90%, let's say. And so you see for 10 node per class, you see they compare it with even with MLP or GraphSage. So they compare their GNN GCN with GraphSage. You see a slight improvement, 2%, let's say. Standard deviation, still the same, similar.